introduction for students. Um, you all must have seen very beautiful color pictures or color objects in the nature. For example, you know everyone that why we see colors. So basically, green leaf or any color things. So that's because it's because selective absorption, because some specific wavelength of light gets absorbed by this object, and the rest out of the white light gets reflected back, and the rest light becomes colorful. So here I have given some examples of those some objects, color objects. For example, these stones, which looks colorful, the peacock feathers, and some butterflies and beetle wings. So why I give this kind of colorful pictures? Because if you notice, when you look at the leaf, green leaf, so it looks green color, whatever may be the angle you see at it. So normally, or at an angle or any angle from distance, whatever, it looks green color. But this kind of color I have shown here, they actually look different color in different directions. That means it's not similar to the usual objects we see as colorful objects like green leaves. So there must be something different, some physics behind this. So let's, for example, take this. Just 1 minute, I will pointers. Yes. So if we see this wing of a butterfly, and if we zoom into it, and we can see that it consists of a large number of some kind of periodic structure or some kind of array. So this kind of array actually is responsible for this color that is different in different directions. When light is incident on these structures, it gets diffracted or it gets some kind of selective reflection. But that reflection or diffraction is actually dependent on this periodicity or this distance between these periodic arrangements, and also the material of this structure. So these are actually called photonic crystal. So if you know semiconductors or any the one we actually study in UG, their electrons actually see a kind of periodic potential there, nucleus. Nucleus is in a crystal, nucleus is actually periodically arranged. So electrons in this periodic potential, when we actually what we do, PG students or UG students must know in their solid state paper. So we solve Schrodinger equation there. So in that when we solve Schrodinger equation, we got a specific solutions known as eigenvalue equations, or eigenvalues, that the energy values, and the eigenfunctions. If you remember, in semiconductors, there is a gap occurs in the dispersion curve after solving these Schrodinger equations. And based on that gaps, we actually classify solids, semiconductors, conductors, and dielectrics. Similarly, if we think light and these periodic structures as periodic repetition of refractive index materials, but just to notice, just to mention here, the periodic potential of nucleus actually in the range of angstrom orders. So the separation between the nucleus is in angstrom. But here, since we are not dealing with electrons, we are dealing with photons. So we are dealing with the periodic repetition of some kind of materials that is in the range of micron or nano range, not in angstrom range. So whatever we apply there for electrons in a crystalline solid or semiconductor, similarly we can apply here to obtain similar kind of eigenvalue equation. So this is, so not only in nature, we can actually fabricate this kind of structures. For example, I have shown here some kind of beautifully fabricated photonic crystals. If the periodicity is along one direction, like here shown here, this is called a 1D photonic crystal. If the periodicity or the arrangement of materials in 2 dimensions, they are periodic in 2 directions, that is called 2D photonic crystal. And if they are arranged in 3D, it's called a 3D photonic crystal. So if you remember in your solid state physics paper, there is a wave called block waves. Electrons in a periodic potential, they are not like plane waves. The waves in a periodic potential or in a solid actually are called block waves. So what are block waves? So if you see this structure here in the left side, there is a periodic repetition of some kind of circular structure. consider these as atoms or consider these as some kind of silicon material that is repeated like this. So it's a periodic structure. A plane wave is incident normally from the top. If you see inside the solid, it's still a periodic wave. It's actually a plane wave. But if you see that this blue color is actually wavefront, the red color is also wavefront. The wavefront is actually distorted, and this wavefront takes on the same periodicity as the structure or periods. It's not like a plane wave, it's a distorted plane wave. Similarly, if you see here, an plane wave is incident on this crystal at an angle of incidence. If you see, the plane wave streams inside these crystals propagates at an angle following the refraction formula, Snell's law formula. But the difference is in air or when there is no periodic structure, it's a plane wave, completely plane. But here, this plane wavefront is distorted. And this distortion takes on the same periodicity as the crystal. So this is called a block wave. So block wave is actually a combination of a periodic perturbation that is called A of R or known as envelope and a phase term that is periodic like a plane wave. So this combination gives a distorted plane wave that is called a block wave. This is for this you all know in solids crystals. Similarly, what we do, we can apply the same concept for photonic crystals. How to get the block waves and also how to get this dispersion curve or band in photonic crystals. Let us think of our solid state crystals just like a FCC lattice. If you see in a FCC lattice, the atoms are at the corners, 8 corners, and there are 6 atoms at the faces. So in FCC, the primitive lattice vectors are like this. There, this T1, T2, T3. So each atom is connected with the face atoms. So that these 3 vectors, and we know this. We can directly convert this to a reciprocal lattice following this formula. So capital T1, capital T2, capital T3 are the reciprocal lattice vector as shown here. This whole gray color spherical kind of thing is actually the reciprocal lattice of this FCC lattice. So this gray color whole patch. But if you consider the symmetry of the crystal, symmetry means we don't need to study the whole unit cell in the reciprocal lattice. This is called the Brillouin zone. We can actually apply symmetry to reduce the size of this Brillouin zone, but without losing any information. For example, the whole gray color patch is the Brillouin zone of the FCC lattice. But when we apply the symmetry, for example, reflection symmetry, translation symmetry, inversion symmetry, then we can reduce this to this yellow color patch of a small volume than the Brillouin zone. This is called the irreducible Brillouin zone. And this irreducible Brillouin zone has certain points known as gamma, L, K, W, U, X. And these points are specific to the lattice which are considering. For FCC lattice, it is specific. For BCC, it will be different. For simple cubic, it is different. So by knowing these symmetry, high symmetric points, gamma, X, L, K, W, U, we can actually study the whole properties of this solid. We don't need to study all atoms. We just need to know these high symmetric points. Similarly, what happens in a photonic crystal? I have shown here a photonic crystal structure, this silver color. And this blue color is actually photons or light that is falling on these crystals. So what happens when light interacts with a photonic crystal? Similarly to the FCC lattice, we can consider this photonic crystal and convert it into the Brillouin zone. And then reduce this Brillouin zone to its corresponding irreducible Brillouin zone that consists of these high symmetric points, gamma, X, L, W, U, K. So if you see here, the blue color is actually a plane wave. It's falling on the crystal. Think of this as a plane wave falling on the crystal. So this, then, as the wave propagates along this crystal, so for example, if you see here, from as the direction changes, we are actually scanning from the center of this Brillouin zone gamma to each point, gamma to L, L to U, U to W, W to X. So what I did here, I placed this irreducible Brillouin zone. Just take those periphery of this Brillouin zone. Don't take the volume. So just take the edges of this volume. Then just elongate this periphery and put it on axis. So just like U, X, gamma, L, K, W, just put it on the axis. So this is actually called the wave vector or K vector of these photons, similar to the electrons in a solid. So now, if we solve, there we solve the Schrodinger equation because electrons are quantum particles. So we have to solve the Schrodinger equation. But here, photonic crystals are not in the angstrom range as I told. They are in micron or nano range. So we cannot solve that. They are not quantum particles. So there we cannot solve Schrodinger equation. What we can solve, if you know, if you study in your electromagnetism or electromagnetic theory, we use Maxwell's equations to study the electromagnetic wave propagation in any material. In any material means it can be glass, it can be aluminum, it can be air, anything. But here, the difference is it's not a uniform material. It's just a periodic repetition or some kind of periodic repetition of materials. So in that case, what we did, we just modified the Maxwell's third equation and fourth equation and convert it to a very nice eigenvalue Schrodinger equation. There, in Schrodinger equation, we use the psi of x. Here, since we are using Maxwell's equation, our psi is here actually electric field or magnetic field. Here, I have used this equation in terms of magnetic field. So left side is the operator operating on this magnetic field, and right side is the eigenvalue equation, and it's the corresponding magnetic field. So when we solve this by eigenvalue equation, that means for each U, X, gamma, L, K, X, W. For each and also in between these, all these allowed K values are wave vectors. So if I solve for each K value, this and this my eigenvalue equation or Maxwell equation, we find a large number of possible eigenvalues or eigenfrequencies. These are called omegas. So if you see here in this photonic band, for each K value, suppose I take this K value, this is another, this is a allowed frequency, here is another frequency, there will be a large number of frequencies. So these are called actually bands. They're actually called bands. So if you see this band, if you see here, there is a gap of allowed frequencies here. That means whatever may be the K values or wave vector, these range of frequencies are not allowed by the electromagnetic propagation of inside the solid. This is actually called a photonic band. That means similar to a solid, in a semiconductor, we have what? Electronic band. So that means we can classify the solids like semiconductors, dielectrics, or insulators, so metals. Here also we have photonic bands. That means when we incident these frequencies or these wavelengths into this solid, there is no solutions at all inside these photonic crystals. That means these wavelengths are actually reflected back. They are not propagating inside the solid. Since they are reflected back, so if we incident a white light, so some of these frequencies which are not allowed, they will be reflected back. That's why we see a color. And the gaps actually depends on the direction of periodicity, because periodicity or lattice constant changes when you change the direction of incident. If A is the lattice constant, if we are incidenting along this periodicity, that is A, suppose 500 nanometer. Now, if we incident under angle theta, it will be A cos theta. So periodicity will be changed. Accordingly, the range of wavelengths that will be reflected back, it will change. That is why when we incident light on a photonic crystal, we see different colors in different directions. So this is definitely different from that of absorption-based color filter colors. So we can even better understand this considering a two-dimensional square lattice here. The corresponding Brillouin zone is here. So this is the square Brillouin zone corresponding to the square lattice. But if we reduce and use symmetry, we can convert this Brillouin zone to a triangle-based irreducible Brillouin zone. Only 3 points: gamma, n, x. So we just the same procedure. We just take the edges and put it on the x-axis, the wave vector. So m, g, x, m, and they solve the photonic crystals equation, the eigenvalue equation. Accordingly, we find a large number of eigenvalues which are allowed and not allowed. And the corresponding field profile when it enters the crystal, it looks like this one. So now, since I told the periodicity can be along one dimension, it can be along two dimension, it can also be three dimension. So accordingly, it can be 1D photonic crystal, a 2D photonic crystal, and 3D photonic crystal. Here I have shown one of the most important application of photonic crystal, that is a 1D photonic crystal, or known as guided mode resonance structure. Suppose we have a 1D photonic crystal, means this is repeated along one dimension only. So periodicity is known as this gamma or A, that is known as the period. This is this is similar to you. You must know this looks like a grating structure. This definitely is a grating. So what happens when light is incident on this? We can definitely solve that Maxwell equation and get the allowed values of eigenvalues what can be guided in this guided mode. But if we don't consider that, just let's go to the simple picture of UG level diffraction picture. What happens when light is incident on this grating? So it depends on this grating equation. The grating equation actually depends on the grating periodicity, what is the period grating, the angle of incidence theta, the refractive index from which the light is coming, and the refractive index of the medium into which the light is going. So based on that, so if you solve this equation, so we will have a large number of diffraction orders. This is all you know in your UG level optics course. So this is called diffraction. Waveguide, do you know? Waveguide means just like optical fiber. Optical fiber now is used in all the internet things. Light is propagating like a guided mode. So consider this as a waveguide. So when light satisfies the total internal reflection, it's guided inside this waveguide like a guided mode. This is actually a ray picture how light is guided like total internal reflection, and this green color is looks the mode profile. So what happens when we put this grating just below the waveguide? What happens? So the light will be refracted. Suppose one of these refracted rod satisfies this guided mode condition. It becomes the guided mode. Now, this diffracted light will be guided along this waveguide. But since the guided mode travels along this waveguide, it again sees this kind of perturbation of this grating structure. What happens? It gets scattered. This light, as it propagates along this waveguide, it sees this grating, again scatters out. Again, it from this grating scatters out. From this grating scatters out. So all these scattered light, they form a resultant wave here. So these resultant plane waves, when interfere with this zeroth order reflection, they all interfere constructively or destructively. So if they constructively, all these scattered waves constructively interfere, just like you do Young's double slit experiment, interference of waves, superposition of waves. All these waves, they interfere among themselves and form a resultant wave. So if that resultant wave is constructively interfering, so we will get a resonance condition or we will get a peak in the spectrum, just like here. So what we do, we incident light from the top, it satisfies the guided mode, it again reflected back. Under a certain condition, depending upon this periodicity, refractive index, incident wavelength, all these things, we will get in the reflection spectrum a sharp peak. And this sharp peak is actually called known as GMR peak or guided mode resonance. You can see this video here, what happens when light is falling from the top. You see here, so the light is actually guided, you can again see, so a plane wave is falling. So we are putting it on the photonic crystal. You see, maximum of the light is actually guided along the waveguide, and as well as it's guiding, as well as some portion is getting reflected back, which is not seen here because of this color pole. So we get a color, we actually get a GMR peak here. If you see here a picture, a glass plate looks like this one. The green color patch is actually the grating structure. So this is a real GMR of photonic crystal structure. We're incidenting a white light on this, and this GMR peak actually we're getting at 500 nanometer wavelength. 500 nanometer wavelength reflected back, we will see a reflection, GMR reflection, which looks like a green color patch. That's what it looks like, a reflection color. So what are the properties of this reflection peak? It's very narrow. You see, the peak is very narrow. It's roughly in the range of 1 to 3 nanometer. And since if you see here, the mode here is actually mode profile of this electric. As it propagates along this grating, the electric field looks like this one. If you see the electric field, some portion of this electric field is outside the grating. So whatever will be added onto this surface, it will be touching the electric field. That means the electric field is very sensitive to this outside medium. That's why it can be used as sensor. So it's very high efficiency, means the peak reflection is almost at 100%. So based on these properties of GMR, there are a large number of applications. It can be used as a spectrometer. It can be used as a filter. It can be used as a solar cell. It can be used as a polarizer. It can also be used as a laser. But one of the most important properties of GMR is biosensing, sensing properties. which is the core of my research. So this can be used to detect whatever DNA or RNA is falling on the sensor surface, protein molecules that is falling on the sensor surface, cells that is falling on the sensor surface, or tissues. It can detect what kind of cells, what kind of tissue, what kind of protein or DNA molecules they are falling on this GMR surface. So how it acts like a sensor? Let us understand this. So this is a GMR sensor, the photonic crystal. If you see here, this is a mode picture. This is the electric field profile. If you see here, some portion of this electric field is actually extended to the medium outside this grating. So when these kind of Y-shaped biomolecules, these are actually biomolecules or biomarkers, protein, DNA, cell, tissue, anything. So they are represented by these kind of structures. When they actually fall on this grating surface, they interact with this electric field. So what happens, since they interact, the electric field profile actually changes. The resonance condition changes, everything changes. So what happens then? So here we can see how we detect them. Earlier, before attachment of these biomolecules, this black curve was there. It was the resonance peak. Now, when we attach these biomolecules on this, the resonance condition changes. So this curve shifts. So if we can detect which shift from this black to red, we can detect what are the biomolecules are actually attached and what are the refractive index, what is the properties of the biomolecules. So this is the overall basic principle of GMR sensor. So based on this overall GMR picture, so we have actually made a device. This device is actually, if you see here a black box here, this is actually a sensor made up of actually a light source, a chief LED source, a filter, a polarizer, a lens. So light falls on this. So we have a beam splitter here. So some portion of this is actually reflected back. So this is the sample. The GMR sample is put here. So whatever reflected back from the GMR, it will be collected by the CMOS sensor. So it's very cheap. Only a CMOS sensor and a LED and some very few inexpensive optical components. They are packed into a sensor box. So this box is roughly in 5 to 7 centimeter in length and also around the same width. So this is the real imaging box. So one of the most recent work that I did. So how to detect biomarkers TNF alpha and IL-6. This TNF alpha and IL-6, these are two biomarkers. These are actually found in when there is a chronic wound. For example, some person has a diabetes and he has a wound that is so that kind of wound is actually contains these two biomarkers, TNF alpha and IL-6. So what we do, we take the wound extracts. We collect this through syringe and I put it on a GMR sensor. And this green color is actually a bandage. Usually we do bandage when we have a wound. So that bandage is actually covered on the wound. So this is just a muscle and skin tissue. So this bandage actually collects these biomarkers. So from this bandage, we collect the syringe, the liquid from this bandage, and we put it on a device with our GMR sensor on top of this. So then we detect the shift in the GMR peak, and accordingly we find the condition of this wound, what are the level of biomarkers. So the sensor that is used, if you see here, it's a grating structure, roughly in the range of 500 nanometer. Second thing is, we did actually put real application in the industry. What we do in industry actually, this is, if you see here, a water pipe, you look like it's water pipe, right? So in the water pipe, water is flowing. So in this factory actually, there is growth of bacteria inside the pipe. We all know, definitely if there is a water, there will be, depending upon the temperature and condition environmental, there will be growth of bacteria. So can you detect this bacteria growth inside this pipe? Yes. So what we do here, if you see inside the pipe, we just open one portion of the pipe and fit the GMR sensor there. So if we put the GMR sensor here and then we try to check the growth of bacteria on the sensor surface. As the time grows, so this is the this x-axis is the time. As the time grows, so this is in hour. So the bacteria takes time to grow. So as you see here, so up to 10 hours there is no growth. Suddenly after 10 hours, the bacterial count actually increases. That means the shift in the resonance peak actually increases gradually. So detecting that resonance peak shift, we actually detected the growth of the bacteria, and that's why this is actually currently under working in the sensor in the factory. It's a pilot project. So now comes to, apart from the sensor, another application is in solar cell application. So solar in solar cells, one of the most important application is use of graphene. Graphene is actually used in solar cells to trap light or to enhance the absorption of solar cell. So if you know, in solar cells, silicon actually it's a photodiode. So it converts the electromagnetic wave to, if the light is falling on this surface, it converts that photodiode the photodiode converts this electromagnetic wave light into current. So, but just like glass surface, maximum of the light is actually getting reflected from the silicon surface. So can we trap the light on the silicon surface? So graphene is actually used as a trapping material on the silicon surface, so that maximum of the light that is falling on the silicon solar cell surface, it can be trapped, and maximum efficiency will be we can achieve. So what we do? So we use this photonic crystal of GMR or graphene. We put this graphene there. You see this purple color, this under the grating and below, just above the grating, waveguide layer. So then we optimize our parameters and structure, and we did a theoretical simulation. Graphene actually does not absorb anything in electromagnetic spectrum. It's roughly absorb only 2% of the electromagnetic waves in the UV visible to NIR. So if you now somehow trap this light using this GMR condition. GMR, you know, maximum of the light is inside the waveguide. You see here, light is actually following in the waveguide, so trapped in the waveguide. So if we put just a graphene layer above this grating, so just below the grating, so the light will be trapped. So if you see here, the experimental core data here, so at 760 nanometer, you see 2% to roughly 65%, 70%. The absorption increased. This is a huge absorption enhancement in field of solar cell. So coming out of this 1D photonic crystal, let's dip into the two-dimensional photonic crystal. So if you see here, it's some kind of flower structure. So these flowers actually, you see, they're arranged in hexagonal structure. It's like, look like a hexagonal pattern. This is a two-dimensional hexagonal photonic crystal. And this flower structure are actually zinc oxide nanostructure. This zinc oxide is a semiconductor material. It's grown on this silicon substrate. So silicon substrate is used like just like I told, a solar cell. So by growing this kind of flower structure on this, just like a photonic crystal, we can enhance the absorption of this silicon solar cell light. So if you see this flower-like structure at the base, the index is high, 2.25. Silicon refractive index is roughly 3. So 2, then 3 at the base of this. This is connected to the silicon surface. So silicon has a refractive index 3, and the base of this flower has a refractive index 2.25. Since the zinc oxide nanoflowers, they are spreading out towards the top, the refractive index, average refractive index, if you calculate, is gradually decreasing. That means from the top of the silicon surface toward the top of the flower, actually the refractive index gradually decreasing. So it's like a gradient refractive index modulation. This is similar to a moth eye. Moth, you know, moth is actually an insect. The insect eye is actually just like it's the same refractive index. This is just inspired by this moth eye structure. Nature's inspired research only. So because of this refractive index graduation decreasing, if we incident the light from the top, so it will be reflected from each of these refractive index at different values. So there will be no sharp reflection from the top surface of the silicon surface. The reflection will be reduced because of this gradient refractive index variation. So if you see here, the green color here is actually the bare silicon reflection. Silicon reflects 40% around of the electromagnetic wave from 300 to 1200 nanometer wavelength. By using this kind of photonic crystal structure, we actually reduce the reflection from 40% to roughly less than 5% or around 4 to 5%. If you see how these actually working, if I increase, sorry, just so if you see here the movie, how the light is actually guiding towards the bottom of the surface at two different wavelengths. If you see here, light is falling. So now the zinc oxide flower is actually, see how light is guided through this funnel. So it is completely trapped inside the silicon solar cell. It's flowing through the channel onto the silicon surface. So this is the mechanism. Now, let's go back to another important application. So this is color filter for display devices. Students, you must have seen color pictures. So how does it looks color? Because just like our eye have these cones, cone pigments like red, blue, green. See, similarly, our display devices, for example, television, any color camera or mobile devices, there are color filters, and the color actually happens because of this some kind of dye pigments. Dye means some chemical molecules are there. So these chemicals actually, if you noticed, when you see the TV screen or towards an angle at an grazing incident, not just normal incidents, you just look at an angle, the color looks different. It's because of these color pigments. And also, when the TV becomes old or display devices, these color molecules, since they're chemicals, they become deteriorate, they degrade. And the actual color actually does not look as it should be. So this is the drawback of color filters. So what we did, we use photonic crystals, just like if you see here, these are the, if you see this red color pillar-like structure, these are actually silicon pillars. They're arranged like a photonic crystal arrangement in VC. They're actually put in a matrix, or matrix means a material, soft polymer, a transparent material known as PDMS. This is a chemical, but this is a silicon-based material. So these silicon pillars actually have different diameters. So if you want a red filter, the diameter of these pillars in the range of 200 nanometer. If you need a green color filter, change the diameter to 140 nanometer. And if you need a blue color filter, change the diameter to 100 nanometer. So by changing the diameter, we designed three different color filters. If you see here, this if you see, this is actually a glass slide, microscope slide. On top of these, three color filters are kept. One is red color filter, one is green, the other one is blue. And the light is falling from the top. It's natural light. If you see here, the corresponding color images looks like this one. The top three are the filters. The bottom three are the color images. When you see, these filters looks like the corresponding colors. And when you see, this is the actual arrangement of color filters inside a display devices. There are actually two green filters, one red filter, and one blue filter. The two green filters are diagonal. This is called a Bayer arrangement. The usual color filter in display devices are actually this kind of arrangement. These are called color pixels. So if you see, we arranged our filters. Blue color filter is giving blue, light is propagating to the blue filter, and correspondingly green and blue are also guiding the corresponding green and red colors. Now, another important application is in optical diodes. You students must have known diodes. Diodes actually in electronics circuit, there are two types of biasing, forward biasing and reverse biasing. So in forward biasing, when we increase the voltage, the forward current increases. So then in the reverse, even if we apply the reverse voltage, it does not increase the current. Similarly, we designed a photonic crystal structure using nanopillars. So this is just a schematic diagram. So when light is in, this is a port 1 means this is the forward direction, similar to the forward voltage. And from here, we collect the light. So forward biasing means we incident the light from the top and we collect the light from the bottom, this portion. And when it's reverse, we incident the light from this bottom portion, and when we collect the light from this top port 1. So we see that when we measure the light intensity, we see that the light is actually increasing the intensity when we increase the intensity of the light. So this is actually acting like a forward biasing diode. So, and in the reverse bias, when we increase the light intensity here, it does not increase the light intensity in the connected port 1. It's because of nonlinear effect, so which I am not going into detail. So this is a very good application in photonic circuit, the future of computation, future computers. Photonic circuits currently having a huge research underway. So this is one component of that. This is optical diode. This can be used in photonic circuits. So this is actually the overall talk and overall research of my my research career. So I'd like to thank research collaborators and the institutions where I have been doing research. University of York, UK. So this picture in my last, I was working there as a researcher in University of York, UK. And ETH Zurich, Switzerland, Rochester Institute of Technology, US. And the next speaker also worked there in the US. He was, we both were working there, Dr. Deepak. And I was working as also in NTU Singapore, in KTH Sweden. I did my PhD in IIT Delhi in optics and photonics. And currently I am doing my research and I'm teaching as assistant professor in Nepal Autonomous College. And thank you. Any questions? Hello.
Sir,
You can call me Pankaj, no problem.
we wanted to know more about the photonic diodes. How do they, what are their applications actually? I wanted to know what are their
Yes.
applications.
So, yes, currently, sorry, am I audible? Hello.
Yes, sir, you are audible.
Yes. So actually, diode is one component in optical circuits. So whatever application of diode in electronic circuits, so we can have replace this in a photonic circuit, not in electronic circuit. So whatever application, for example, photodiode as a spectrometer or in on-chip spectrometer, that means we can design similar kind of diodes, a large number of diodes. So it will be we can have light incident on this, and only output will be from this side. So it will be not be in the reverse way. The same application of electronic diodes. So whatever for current in diodes, in electronic diodes, same for photons in this photonic diode or optical diode.
So here, the intensity of transmitted light depends on what? The intensity of light, or
yes. So I'll
voltage?
tell. No. There is no voltage here. Nothing is related to current here. So actually it's here. So if you see here, this R1 and R2, these are actually two ring resonators. So ring resonator means when light propagates along this axis, it couples to these resonators. And what I did, this ring resonator actually made of nonlinear material. Nonlinear material means they're independent on the intensity of the light. So when the light intensity changes or increases gradually, the refractive index actually changes. Because of this nonlinear effect, if you see the formula here, delta N equal to N2 into I. So N2 is the core coefficient and I core coefficient is the nonlinear coefficient and I is the intensity. So the refractive index, since the refractive index changes with the intensity of the light, so it gradually actually increases the intensity of the light. But here, actually, we have blocked the forward propagation. In the reverse case, when light is incident from this side, we are not allowing the light to go to this resonator. So we are allowing only light to here only. So that's why there is no role of R1 for this reverse bias condition. So it's just not working for the reverse case.
How it is different from
okay.
Wait, I have a question.
How it is different from?
How it is different from
Yes.
a unidirectional flow channel where you have only one directional light flow, whereas when you come in the reverse direction, you don't see any intensity out. So it's just a one-dimensional filter kind of thing. I can say that. So,
No, it's two-dimensional actually. It's two-dimensional. Actually, in the
one
reverse case, we are incidenting light from this port 2 and collecting light from port 1. So whenever we are increasing the light intensity from this side, whatever may be the intensity increased, it's not going to be here. Light is not coupled to this R1. Light is only coming reflected because of this photonic band gap. It will be coming back from this channel. It's not coupled to this R1. So it's actually bidirectional, but it's not working from the reverse direction. If
So in
you
the
see
reverse,
here, light is going from here. There is no photonic band gap along this direction. It can go here. It can couple to R2. But here, when light is coming from this direction, it sees the photonic crystal here, so it will be reflected back because of this photonic band gap.
oh, in the reverse case, it will only collect to the ring 2.
Yes,
It
yes.
will couple there, then it goes through and collected at port 1.
Port 1, yes.
Okay. And if you
Yes.
want to do some polarization dependent thing,
Yes, so actually, so the polarization here actually for this for a planar photonic crystal, there is no role of polarization. So we are actually dealing with TE and TM mode. So polarization means it's incident polarization, but we are actually dealing with modes. So TE mode or TM mode. So if the electric field is perpendicular to the screen, then this is TE mode. Its photonic band gap will be different. And if the electric field is in the plane, this is called TM mode. And its photonic band gap will be different. Accordingly, we have to choose the incident wavelength. So for TM mode, a different wavelength will work. For TE mode, a different wavelength will work.
Thank you, Dr. Pankaj, for your nice talk. Sir, I
Welcome,
have
sir.
a doubt. In the slide of fifth, sir, can you go to the fifth number? So the Maxwell's equation, that is going to be a Laplacian, sorry, a Poisson's equation, right?
Yes, sorry, this is not Poisson's equation. This is an eigenvalue equation. We are not operator operating on magnetic field giving eigenvalue, and then yes, we are not doing the wave equation. We are dealing with an eigenvalue equation. Maxwell equation, wave equation is Laplacian, del square of E equal to something. But this is not a wave equation. This is a eigenvalue equation. We're just trying to find the eigenvalues and the corresponding mode. Mode means h of r or electric or magnetic field, but we are not trying to find the wave solution. We are just trying to find the eigenvalues, omega, frequencies, or wavelength, or energy, and the frequency, sorry, the eigen modes, that is the field profile, electric field or magnetic field. The wave equation
Here the
actually
H is
Laplacian.
the
Magnetic field.
magnetic.
Yes. Yes.
Sir, another doubt is, sir, you did the simulation by the FDTD method, right?
Yes. Yes.
Summarized.
Yes.
Sir, we are solving the which equation exactly?
This equation actually. We are solving this equation. We are actually in the FDTD. We are discretizing the time and the space. Space grid. We are making it small pieces. If you know, in time like T1, T2, T3, delta T spacing, and then at each of these pixel or each of these grid, we are calculating this magnetic field.
Thank you, sir.
Welcome. Any more questions?
hello?
Hello.
Yeah, if you go to the zinc flower slide, JDNO flower slide. Yeah, here the bottom one is what, like this, these are grown on
Silicon.
So the waveguide part is just the gradual variation of refractive index. Like
No. Yes. No, there are two. If you see here, I have written here for wavelength of 450 nanometer, and here actually 1100 something. It's actually somehow the wavelength typing mistake. So it's actually I didn't forgot to mention. It's around 800 or 1000 nanometer. So there are two different mechanisms actually. For small wavelengths, the light can travel in each of these nano airs. But for large wavelengths around 1000 or 900, so it cannot be guided in each of these nano airs. They will be guided. The whole funnel will act like actually a guiding vector. If you see here, the top and bottom, or large wavelengths, the whole funnel is actually guiding. But for the small wavelengths, each of these nano wires is actually guiding. So there are two mechanisms simultaneously working.
No. What I would suggest to look at the mechanism is like when light falls on such a structure which is like open in all direction. So there is a lot of chances that there are in-plane scattering. So those in-plane scattering is actually responsible for reducing the reflectance. Same thing happens in moth eye and other structures.
Yes. So scattering is there. Yes. So it's combination. So light is also guiding through this channel and also through the funnel. And also there is a scattering from each of these unit bases.
Yeah. So it will be a combination of all.
Combination of all. Yes.
Okay. Thank you.
Welcome. Any questions? Any questions from students on basics? Any questions from student side? Any on basics? Because I skipped overall everything for research part, just for students. I expect some questions from students, please. Okay, then if no question, then I will go for class. Hello? Hello?
Thank you, Dr. Sahu.
Yes. Thank you. Thank you very much. So I will be logging out.
No, you can definitely stay and listen to the talk of Dr. Raut.
Yes,
He will
definitely.
be speaking right after you.
Okay.
So thank you, Dr. Sahu, for your
My pleasure. Thank you.
presentation. As to our students and teachers alike are very much delighted to have you with us. So I hope in future you'll be joining us more often. I definitely look forward to invite you physically. So
Thank you.
I
Thank you very
hope
much.
in a few months you can join us here.
Thank you. Thank you very much. My pleasure.
Thank you, sir.
So I will stop sharing. So already stopped. Okay.
Dear students, now I am going to introduce Dr. Deepak Raut. He is from Sundargarh, Government College Sundargarh, acting as a assistant professor of physics. So he is also from our state only. He is from Jagatsinghpur district, and as I had already said you, he is my batchmate, my classmate. So Dr. Deepak Raut completed his post-graduation from Utkal University, then his PhD from IIT Kanpur. Then he went into do post-doctoral research work in Pittsburgh, USA, and then again in IISc Bangalore. So his research is also in the field of photonics. So he has numerous research papers in top journals. He has also received many awards and honors like Mukhyamantri Research Fellowship Award 2023, and he is a brilliant researcher. So I again welcome Professor Raut. He will be delivering his talk. Welcome, sir.
Yeah, thank you. Am I audible?
Yes, sir, you are audible.
And my slides are shared, the screen.
Yes, sir.
Okay, so a very good morning to everyone present here and on the other side, because I am sitting with our students also. So I thought they would join and get some knowledge. And first of all, I thank the Department of Physics and the administration of the university for putting up such a nice event that would be useful for the students, and we should have more often this kind of talks and all to improve the knowledge and give students some exposure that is little different from the textbook. So without any further delay, I would dive into my talk. Unlike the previous speaker, I have kept the talk very basic and hopefully useful for the student perspective, but the research part you'll find very less. So you may find it very trivial, but I would try to give a different perspective. So the talk goes like this. I would introduce the Fourier transform and diffraction imaging in understanding crystal symmetry. So when I say crystal, what I mean is actually the kind of periodic structures or photonic crystal that Pankaj was talking. So those kind of structures I'll introduce. Now, this is the outline of my talk. So I would introduce or I would talk about what is Fourier transform and a little bit introduction there. Then I would go for the Fourier transform in the context of an image. We all know how the functions are getting transformed under Fourier transform and what information we get from Fourier transform of mathematical functions. But transforming an image and getting information out of it, it is bit tricky. So we will discuss that. Then how one can reconstruct the image from the Fourier transform image, and then the basic mechanism of optical diffraction and understanding the diffraction pattern. I would like to connect or make a connect between this diffraction pattern and the Fourier transform image. And finally, I would conclude with saying correlating the optical diffraction and Fourier transform image, and how in a laboratory setup like a government college like us or a state level university, how one can use these techniques to characterize the periodic crystal or any pattern that we have. So basically, it would go in that direction. Now coming to the very first slide, so I would like to revisit the textbook knowledge that we have. Whether you would talk of Fourier transform or inverse Fourier transform, we have a function f of t that we want to Fourier transform it into the frequency domain, and this is how the Fourier transform is defined. And if you go for the inverse Fourier transform, you just add a 1 over 2 pi and swap the two functions, and you get the inverse Fourier transform. So when you understand this, as a physicist, we would like to understand what is the mechanism that's happening there. So it is basically the mathematical technique that transforms a function from time domain to frequency domain. When I say that, I mean that it decomposes the signal into different frequencies, so that anyone using this would know how many frequency points or how many functions of different frequencies have been added up or superposed to give me that particular function. So this kind of information we get, and this information is very useful and to reduce the noise or cancel the noise in signal processing. And just simple, like when you would see while people are recording in the YouTube videos, they have a lot of different frequency noise and all, so they cancel out the noise using this kind of technique. Yeah, is it okay? Hello? Hello?
Okay, please carry on.
Yeah, I heard some background noise. So this transformation is useful in signal processing, basically both in physics and engineering. That is the part. But we also know that this particular thing can be used for image reconstruction, as well as how we are going to use it in defining the crystal symmetry. So these are the basic thing I would talk about. Now, going further into like what these formulas which I showed here in f of omega or in f of t, how or what does that mean for a physics student? Now, if I look at these two waves here, I am showing these two waves. Let's say I have a pink wave, I have a yellow wave, and these two are different in terms of their frequencies. So one is of 2 Hz, one is of 3 Hz. Now, if I transform this into the frequency domain, I would get a peak here that is corresponding to 2 Hz. Similarly, here I'll get another peak that is corresponding to 3 Hz. But when I add both of them together, I would get a resultant function, something like this, and I get two frequency here. That is the constituent frequency of these two waves. Now, imagine if I don't show you this purple or the yellow waves, but I would give you only this green wave and tell the students that give me how many number of waves are constituting this particular green wave, and give me the number of frequency, the amplitude of each wave, and those things. So then it would be very complex problem for the students to look at. But if somebody knows the Fourier functional form of this particular graph, and then they do a Fourier transform, they would easily show us that what is the frequency and what is the amplitude part, and how many different waves have been constructed or have been used to construct this green wave. So that is the power of the Fourier transform. Again, further, if we are adding a wave of frequency 1 and 3 and 5, then we add it together and it gives us a signal of a little bit square wave type. And further, when you decompose this square wave pattern into the Fourier transform, the frequencies, individual frequency points, they stands out clearly and distinctly, so that you know these are the points, or these are the frequency of waves that have been added together to give us the resultant square wave pattern. Now, with this information, now let us go to the image or Fourier transform of an image. Now, what I talked previously, it was all about the function. Now, how one is going to correlate between that function with this image. Because in both the cases, previously also we were doing Fourier transform. Now, also we are trying to do the Fourier transform. Now, looking at the image that we know, any image we see, we just know that the minimum possible reduced size is a pixel size, and the intensity pattern is distributed on each pixel. And depending on the content of intensity at each pixel, we see a brightness or darkness or grayscale or even colored image, all these things. So for each pixels, if the color content, depending on red, green, blue, how much of content of red or green or blue are there, they will add up to give us a grayscale image or a white scale image or even lower intensity images. So if we have pixel information and each pixel, what is the intensity, those information are there, then we can go about the Fourier transform, go about doing the Fourier transform and bring out the exact information of pixel wise. And then further, we can reconstruct that image from the raw image. So basically, the Fourier transform decomposes an image into its constituent frequencies, allowing to measure how each frequency is present in an image. So when we are talking of the frequencies here, it's actually the pixels, they are containing different intensity points. Now, frequencies refer to the rate of change of pixel intensity, as I mentioned earlier, how the intensity on a pixel changes. And interestingly, the low frequency points correspond to smooth uniform region in a picture, whereas high frequency points are the drastic and delta function kind of changes in the intensity. So now when an image is there and we have smoothly varying intensity, and we also have very drastically changing intensity pattern, then when they are added together, if we could somehow remove the high frequency points or the finer details or sharp transitions, then we may get a very good image. Now, when we take a raw image, you see it's a grating pattern. Again, it is done with a lithography, technique, and it is silicon nitride on a glass slab. So when you do something of this kind, and this is again electron microscope image of that grating, and that this is fabricated in the Indian Institute of Science. Now, when I take this image and take the Fourier transform, I see a line-like pattern in the bottom. And hope you are seeing the pointer option when I'm moving. You see there is a distribution of black white spots. Now let's go further into it. Now this was the raw image, and this is the Fourier transform image in the middle. When I take the Fourier transform, it's just the distribution of the pixel intensity. Now when I do the inverse Fourier transform, I take this Fourier transform image and I do a inverse Fourier transform. What I get, the image exactly like this, but it is now more clearer. When I say more clearer, you see the contrast, you see the changes in the black and white portions, it is clearly visible. So clearly the noise reductions has been done. And as we told here, that the noise corresponds to the high frequency points, and the high frequency points are actually pushed out to the edges. So it clearly it selectively chooses those low frequency points which are smoothly varying and gives us the image. So that's why it's a kind of reshaping of the image by reconstruction of the image from the Fourier transform. And this Fourier transform image is no foreign material to us. We have seen this kind of image like this. So if I take a diffraction grating, just a linear diffraction grating, and I shine a laser light on it, I would get the diffraction pattern from here. So I'm trying to correlate here. You see the linear gratings here, they are arranged in one line. And when you take this and put it under the laser light, you would see a diffraction pattern. So there must be some correlation, because if I change this orientation of this grating, definitely the pattern will change. And as we move into further details in my talk, we would see actually that is what's happening. And from there, we are going to make out, or we are going to see what is the connection between the crystal symmetry and the diffraction pattern. Now, before going to that particular connection, let us discuss, or let us introduce the basics of diffraction. So it's again, the students might have studied in their second or third sem of UG and +2. So I'll revisit the concepts there. So this diffraction phenomena actually results from a wave characteristic. So if light was not a wave, we would never see the diffraction characteristic. Now, what happens to light? That it's a wave, that is why it is diffracting. The diffraction property comes from the very own Huygens principle, which says that on a wavefront, each point on the wavefront act as a secondary source of generation of secondary wavelet. So each point on the wavefront is a source of generation of another wavelet. Now, when the primary wavefront meets the slit or a shaft edge, then the point where it is meeting, there also there will be a wavefront generated from there. So that is why the light bends. So that is, the slit influences the wavefront of the incident wave to change its direction. So this wavefront changes actually brings out the bending of the light, and that bending is actually going into the geometrically shadow region. Now this is for one single slit. If you see the right hand side, the top one is for the single slit, but you keep on adding slits one by one across this vertical line, you would get different interference patterns, because each slit will have its own diffraction pattern, and they will superimpose with each other to give you a final interference pattern, and that would be coming like something like this. So that was the basic understanding how it is happening. And just you put any wavelength of light on any slit, that will not going to diffract, that is not going to diffract. So the way they are related is the wavelength must be comparable to the slit width. Now, the diffraction grating that we see in the laboratory are not the only one we are having. Nature was also very kind to provide us some diffraction grating that we can get. So if you see the right hand side, this is a opal structure or a gemstone structure. It is showing you different colors. And also if you see the peacock feather or butterfly feather, you see different colors. So those are the pattern photonic crystals. They are made naturally. So we can actually mimic those structures in laboratory framework. And in a laboratory, you can also draw lines on a dielectric material or dielectric slab to get a 1D grating. And this is something else. This is a two-dimensional grating structure fabricated with using polystyrene spheres. That is in the next slide you are going to see what is this structure made up of. But that structure, when you put under white light, you see a nice circular pattern, and each line is, or each color is now distinctly separated from the other and spaced at a different radius. So the phenomena is again based on the Bragg's law. The wavelengths that are comparable to the interplanar spacing, they would constructively interfere, whereas the ones which are not comparable, they would destructively interfere to give you minimum intensity. Now coming back to the structures that I showed. So we take some colloids, and these are polystyrene colloids, just simple polystyrene colloids dispersed in water. So you make a colloidal suspension and make a two-dimensional array of those colloids on a water surface. Then slightly lift up that onto a substrate, and this glass substrate on the upper part I am showing, those are used to lift up this colloids which were just floating on the water. Again, if you put the colloids on the water, because of the gravity, it will go and sediment at the bottom. But if you do the surface tension engineering by adding little bit of isopropyl alcohol on the top, then the surface tension of water increases, and when you disperse or drop your colloidal suspension on a water level on a container, you can think of a bucket or on a glass water surface, you add some propanol, then put the colloidal suspensions there, it will float. So when it is floating, you just insert a glass slide underneath and try to lift up without disturbing the surface. Then after drying, you would get some colloidal crystal like this. Then you take it to the electron microscope, and you see the periodic arrangement of the colloids here. And this side, what I did, or what we did rather, is we poured the silica solution onto this. So silica is a hard material. When you dry it, it becomes hard, and then we removed this one, the polystyrene. Polystyrene is easily can be easily removed by any acidic medium. So we used the sulfuric acid and hydrogen peroxide combination, that is the Piranha solution, to eat this polystyrene colloids, and you get a nicely 2D array of inverse structure. And this, the only like motivation to do this was, this is just standalone polystyrene colloids on a substrate. So anytime any application of force, it will distort the crystal and it will fall off. But once you make it with a robust silica structure, then it's robust there. It is not going to go unless you are breaking it. So here the white portions are here are the silica interconnects, whereas the black portions are just the air holes. Now, when you take such a structure and put a laser light of comparable wavelength, or which can undergo diffraction, then you see the transmitted light is giving you some 6-spot pattern. Now, when we put pointers exactly how they are getting arranged, you see the diffraction pattern and the colloidal arrangement here have hexagonal symmetry. And this hexagonal symmetry is due to the hexagonal symmetry seen in the diffraction pattern is due to the extra hexagonal symmetry of the structure of the structural arrangement of the colloids on the glass surface. So if this was not hexagonal in geometry or in arrangement, we would not get a hexagonal pattern here. But it is very early to conclude that. Now let us do the same experiment for our other inverse crystal and what we are going to see. So it is exactly the same way. We took out that crystal and insert this crystal and we shone the laser light, and we recorded the transmitted diffraction pattern, and we see again a 6-spot, and it is much more clearer. You see there are other points, other intensity points at the intermediate between these 6 spots, but here it is clearly a 6-spot pattern, and when you see the hexagonal thing, it's also there. Here the unit cells are now different. Now what we again trying to prove here is, we are trying to show that the colloidal arrangement or the crystal arrangement has direct correlation for the diffraction image that we are getting, or diffraction pattern that we are getting. So here the Fourier transform comes, and it actually helps, and it is like a complementary thing. It complements the idea of that the crystal symmetry and the diffraction pattern are actually related. So how do we take this image and also the inverse structure, and we take the Fourier transform of these images. And when you look at the Fourier transform and see both the bottom images here for the inverse structure and the direct structure, we see nicely arranged 6-spot pattern or hexagonal pattern. So when you try to join them with hexagon, these are nicely joined hexagonal pattern, and which has correlation with the measured diffraction pattern as well. So this is a clear indication of how the crystal symmetry can give you different diffraction pattern. The point is, if I change the orientation of the crystal, this diffraction pattern will change. Now we would see in further slides so how that is happening. So these structures that we decided are the 2-dimensional colloidal pattern on a glass slide. But if I take a 3-dimensional crystal, again this is done by self-assembly method, where we have multiple layers of colloids arranged one on another, and then we pour the silica salt into the pores, and once they are hardened, we again put the whole thing into the piranha solution, then such that we remove the polystyrene. So once the polystyrene bits are removed from the crystal, you see there are just a scaffolding of silica matrices which are containing the air spheres. Now you take such a crystal and take the Fourier transform. This again gives you hexagonal pattern of dots. And when you look at the diffraction pattern for coming from such a crystal, you see a 6-spot pattern, and where the central spot is again the directly transmitted light. So looking at the images and diffraction experiments so far with different colloidal diameter, here I have put all the scale bars. So here the colloidal diameter is 140 nanometer, and here it is kind of 1 micronish kind of diameter. And so depending on the diameters, the wavelength of the incident light changes, and we see different diffraction patterns or different diffraction intensities, diffraction points, but the pattern remains the same. Here it is hexagonal, and previously also we saw these hexagonal patterns. So the pattern does not change. Now what is the connection between them? So to know that, what we did is we tried to design an experiment where we are rotating the crystal constantly. Now the idea is, based on the symmetry, if I rotate the crystal, if the diffraction pattern rotates, then I know that the structure and the diffraction pattern has to correlate with each other. Otherwise, the diffraction pattern will not rotate. So here I am showing a rotational symmetry of diffraction pattern by rotating the photonic crystals or colloidal crystals that we do experiment with. So I am taking, because all of them are looking similar, so I put just a red dot along one of the arm and rotate it 60 degree. So when I rotated the 60 degree, this arm rotated by 60 degree. Then when I further rotated it another 60 degree, this is rotated by 120 degree. So the kind of rotation I put for the colloidal crystal, the same kind of rotation I get through the diffraction pattern. So this pattern actually was measured. This proper lines are drawn, and you can measure it with protractor and any other kind of sophisticated angle measuring devices, and you would find this is more or less around 60 degree between each of these arms, and that is exactly how the hexagonal symmetry retains its rotational symmetry under the rotation. So if you rotate it by 60 degree only, they are going to appear as its previous counterpart. So 60 degree is the rotational symmetric angle for a hexagon, and under 60 degree rotation, we are, or the pattern which we are observing, that appears exactly the same. So that is clearly visible here. I'm going to show the movie here. Here what we did, we have the crystal mounted on a optical mount, and then we shine the laser light onto it, and the laser wavelength is around 213 nanometer. So when the laser falls on it, at that time, once we see the pattern, we rotate the crystal, and once the crystal is rotated, So here you see there's a slit here in which we have mounted the crystal at the black line. Let me go to the pointer option. So here, somewhere here, it's very dark to see, but somewhere here we have mounted the crystal and we rotated the crystal while recording that pattern. So we saw that as we rotate the crystal, the pattern rotates by an equal degree of rotation. So this kinds of confirms, or this kind of confirms that the rotational symmetry or the diffraction pattern and the symmetry of the crystal, they are related. Now imagine if I do not have this hexagonal symmetry of the crystal, but rather I have a square array of crystal, square array of spheres or square array of inverse structure arranged in a crystal, then I would get a 2D diffraction pattern which is like a square pattern. So if I rotate it by 90°, the pattern will also rotate by 90°. Similarly, for 1D crystal or 1D diffraction pattern that I showed earlier, if I rotate it by 180°, then only I'll get back the pattern. So the rotation angle of the crystal directly depends on what symmetry it has, and same thing transforms into the diffraction patterns symmetry. So based on this, we can conclude that the diffraction pattern and crystal symmetry are related, and further how to relate the Fourier transform imaging into determining the crystal quality. So we took different images of same crystal, where one of them was having a little bit higher level of ordering, and whereas others are not so good in the crystal ordering. You can see that the structures are broken in the middle, and even in the extreme right, the structures are broken in the middle. Now, when you take the Fourier transform of these images, if you see the bottom part, at the extreme left, you see nice hexagonal patterns like this, but here you do not have any hexagonal pattern to look with, but here it is a circular pattern. So this circular pattern is sometimes called dividing. This is because of there is still crystal symmetry or rotation, but they are arranged in different grains. So if you look at where I'm moving the pointer, that is one crystallite. This is another crystallite. This is another crystallite. This is another crystallite. So if I look at the average orientation, all the crystallites are oriented in different directions. So when I took it together, then it acts like a average orientation. So that's why you get a hexagonal spot, but that is lying on a circle. But here you don't see anything. So combining all this together, what we can conclude is the Fourier transform imaging along with optical diffraction provides insightful information about the crystal symmetry. And this method is highly cost effective, and we can use it for any laboratory experiment. And simple diffraction experiment can give us understanding the theoretical and experimental physics. And obviously, again, to remind, these crystals, the dimensions are in micron or nanometer, like 500 nanometer or 200 or 300 nanometer. It is not the crystals that we study in the textbook, that is the solid state, where the periodicity is in the angstrom order. But these things, the grating things, we can design it in the nanometer and micron order. Yeah, so with that, I would like to conclude, and thank you for your attention. Yeah, if there is any question. Hello?
Thank you, Dr. Rao, for your this nice presentation. Sir, the simple question is, sir, when the raw images go through the Fourier transform, sir.
Yeah, I can hear you.
Yes, sir. When the raw image go through the Fourier transform, again when we do the inverse Fourier transform, again we are getting the same raw image but we are getting a clearer image. Why it is so? How is that,
Yes.
sir?
So it is
Yeah,
not the raw image. No.
sir.
Yeah. So I'm audible, right? Hello? Hello? Hello?
Yes, yes, you are audible.
So if you look at the right image and the left image, look at the kind of contrast you have and look at the kind of background you have. In the grayscale image, the inverse Fourier transform image is a better one compared to the raw image, because I can see clearly the contrast between the images. And if I have to measure, let's say I have to measure the periodicity here. If I measure it here, I do not have, I have a gap in the in realizing what is exactly the contrast. But on the other side, you see there's a clear distinction between the black background and the white patches or the white grating. The white regions are the filler and the black are the empty portions. So there is a clear distinction between the background color of black and white. But on the other hand, if you see, you don't see really like that there is a nice hazy background which is overriding the whole of the pattern. So if you want to remove that, this is just one of the images. And if you take any other image, any real-time image, any photographic image, if you do the Fourier transform, you would also see and take the inverse Fourier of this, you would see a good contrast and brightness image. So image quality would improve because you are redistributing the intensity per pixel, and you are seeing you are removing the noise from each pixel. And noise are those actually which does not give us a clear idea of how much content of each red, green, blue are per pixel. So if we don't know about this pixel contents, we won't be able to see a good a good image, or yeah, we won't be able to see a good image. And specifically, I would like to bring in another point here. So specifically, let's say you are imaging a cancer cell or cancer tissue, okay, where the cancer cells are not like delta function, like they are not spread. They are spread like gradually they are spreading. So you don't know, there will be in the boundary or in at the interface where the cancer cell is just ended, the cancer area is just ended, and where there is also good cells are there. So in between there is a gradual change in the content of or the amount of cancer cells into the good portions versus the infected portions. So how we are going to get that information? So if you take the tissue image and then do the image engineering by Fourier transform and doing inverse Fourier transform, you would exactly know from the contrast and all. Okay.
Can I interrupt, Dr. Deepak?
Yes, yes.
So I'm just I think the audience asked about the reason for are we doing something deliberate to remove the high frequency points, or it's just the automatic removal of high frequency points when doing the inverse Fourier transformation?
No, So Fourier transform image, what it does, it arranges the frequency content accordingly, right? So then you
Yes.
can play with the parameters to
Yes,
shift.
so that is okay. So the contrast increases because you are saying the distortions are because the distortions corresponds to high frequency points. So are you image processing or doing computationally to remove these points, or just people in automatically does this?
The Fourier transform automatically does this, but the computational, you are saying you have to write the code for this and using the algorithms of the Fourier transform. The same.
So
same
yes,
process.
in the algorithm, are we writing code to high frequency points, or just writing just doing the inverse Fourier transform and it automatically does?
In this case, it automatically does, but you can.
We are just doing the Fourier transformation, then inverse Fourier transform. So there is no loss of any information or nothing addition, no modification. How just mathematics does remove some information, high frequency points? Simply take Fourier transformation of a function f of x, it will be f of t, and we take the inverse Fourier transform of f of t, it will give the f of x. It should be same mathematically. Suppose Fourier transform of sin x, it gives something else, then we just reverse it back, it should give the same. So we must do something to remove the high frequency points from our own intentionally. Otherwise, how it will automatically do the removing high frequency points?
No. It's not automatic. See, Fourier transform will change. It will give it will decompose it into different frequency points, right?
Yes.
So
yes.
the background noise and all, they correspond to the high frequency. So they automatically.
Yes, we have to remove the high frequency point.
Yes. So that is what when I said you have to write the code and all. So depending on.
Yes. So it does not do automatically. We have to write a code to remove the high frequency code points.
It is not automatic.
Yes, that is spatial filtering. Yes.
Yes, this is the spatial filtering. Yes.
Yes. Any question?
Any question?
If no, can I ask one question?
Yeah. Go ahead.
Yes. So in slide number 8, if I remember correctly, slide number 8. Yes. Here. So I have one basic questions. Maybe it's it should be in the student's mind. Which is the basic interference or diffraction? Interference causes diffraction or diffraction causes interference? Suppose we are considering the single slit diffraction. So the diffraction, why it is spreading actually? It's not interference making the diffraction or diffraction making the interference. Which is the basic? I mean,
diffraction basically. Diffraction. So diffraction
is actually, so in just like in second double slit. So diffraction is causing to bend, then the interfering to give the interference pattern.
Yes.
Right. But what about the first single slit? There is no second slit. Why does it bend to that side? Is it not that every point interfering with its own eigenpoints?
And that's it. The high. Yeah. So
why we are getting the diffraction pattern? There must be something on the.
This is just a demonstration of the wavefront propagation. So when this plane wavefront goes through the slit, based on the geometry of the slit, it's a point source. It's acting like a point source. Now, when there is a point, the wavefront will be spherical. So once we are showing it in the 2D, it will be like a circular. So the wavefront is spreading like the arc of the circle. If you see on the right, left side, we are just giving the input as plane waves. If I do not have that slit so narrow or so small, if I open up that slit, the same plane wavefront will go to the other side. So it is basically the dimension of the slit that is making the plane wave looking like a point source, And because the point geometry, it is spreading like point waves, spherical waves, and in planar geometry, it is looking like a circular wavefront. Yeah, only this much. But the second image gives you more clarity. When you add one more, then those circular wavefronts interfere with each other to give you the diffraction pattern. The diffraction pattern is actually here. You look at the second, and that is, you see the radially going outward patterns, no? So those kind of lines, look at the pointers here. So this way, the angular.
But in single slit also there is a pattern in the screen.
That's at the edge, very, very edge, right?
Yes, what is the cause of that interference? So
Again, it is the if every point on the wave front is a source of the secondary wave.
yes, so that means interference. That means interference is the basics.
No. If that slit was not there, then it will not diffract. If I remove the slit, why you are going? How you are going to see the diffraction? Right. So that pattern is there because I have diminished or reduced the size into a smaller geometry. If I increase the slit size, then there is no diffraction. Hence, you won't see any interference. Again, this can be debatable.
Even if the beam travels in free space, that also expands.
That expands, but that is not interference.
The expansion is because of what? Why it's going sideways?
That is different. That is dispersion. When the light travels in different.
No. Dispersion is something refractive index dependent. It's okay. We'll discuss later.
So dispersion, scattering, these multiple things can add up. Like if the light is traveling in a free space, and if that light is originated from a laser pointer or a torch, so because of the aperture edges, it will diffract, and as it travels, it will expand. But if it is coming from very far point like sun or somewhere, then it will never diffract. It is based on its source, size, and origin. It will just propagate and it will just spread, or we call it divergence. So for diffraction, you need some kind of scattering. Okay, let's put it this way. Scattering is fundamental. Okay, so we can get diffraction and interference from there. The scattering is the more fundamental.
Okay.
And we can discuss more on this.
Sure. Thank you.
Any more questions?
Thank you, Dr. Raut, for your very lucid explanation. And I would also like to thank Dr. Sahu for this lively discussion. Thank you, both of you, for joining us today. And I hope in future you will be joining us physically. Thank you, sir. I would like to thank all students and teachers present here for patiently listening. And I think you must have took away a great deal of knowledge from this seminar. Thank you all.
Yes. Thank you.
Thank you. Bye-bye.